Hi, this is Professor Evans. This video is for EET 1214C, and this video is going to cover series parallel DC circuits. So our learning objectives for this video are that you will be able to apply Ohm's law, KVL, and KCL to a series parallel circuit, and that you will be able to calculate the equivalent resistance for a series parallel circuit. The lab that corresponds with this video will teach you how to measure the total current, the resistor currents, and the resistor voltages of a series parallel circuit on the bench. So first I'm going to do some review. In a previous video, I discussed how we apply Ohm's law to a series circuit as well as a parallel circuit. So I'm just going to review those concepts right now. When we use Ohm's law for a series circuit, we know that by definition, the current through any of the resistors is the same as the total current in the circuit. Again, this is for a series circuit. So we know that with a series circuit, there is one total current that flows through each element. And we can find that total current by using the applied voltage and total resistance along with Ohm's law. So we can add up all of the resistors to find a total resistance, and then we can take the voltage source divided by that total resistance to get the total current in the circuit. That total current is also equivalent to each resistor's current. You can find the voltage drop across any of the resistors by multiplying the total current by the resistor value. And again, that total current is equivalent to the current through each resistor. There is a polarity associated with a voltage drop across a resistor. Remember, when you're drawing your polarity, the positive side is where current enters and the negative side is where current exits. Polarity is important because it indicates the direction of current flow. If you've ever placed a battery inside of an electronic device backwards, you know that the device won't work because the battery has a positive terminal and a negative terminal. So polarity is important, and that's a practical application. So when we label our polarities on our circuits, it indicates the direction of current flow. And again, the positive side is where current enters the particular element, and the negative side is where current exits. We also talked about Kirchhoff's voltage law in a previous video. Here's a quick review. It says that the algebraic sum of the voltage drops around a closed path will equal the voltage applied to that closed path. Or another way of thinking about it is the algebraic sum of all the voltages, both your source voltage and your voltage drops, around a single closed path must be zero. So here's two examples of that KVL principle. We can see that if I have a series circuit with several resistors and I add up the voltage drop for each one of those resistors, it's going to equal the source. Another way of thinking about it is traveling along this closed path and adding up each voltage as you go using each voltage's polarity. So if I were to travel along this loop, I'd have a positive voltage for V1, a positive voltage for V2, a positive voltage for V3. All of these voltages would be positive, and as I go around the loop and hit the source, I have a negative source voltage. So I'm going to add all of these up, subtract the source voltage, and I should end up with 0. That's a review of KVL, Kirchhoff's voltage law. We also talked about Ohm's law for a parallel circuit. The defining characteristic for a parallel circuit is that the voltage across any parallel resistors is the same. And we can find the total current in the circuit by using the applied voltage and the total parallel resistance. Remember to review the formula for calculating the total resistance of resistors in parallel. We want to combine all of those resistors, and then once we do, using the formula for parallel resistance, you can find the total current in the circuit using Ohm's law. Then you can find the total current through any of the resistors in your parallel circuit by, again, using Ohm's law. In a parallel circuit, all of the resistors are in parallel with each other and the source. They all have the same voltage. So I know the voltage across each resistor, and I can use Ohm's law right here to find the current through each resistor. And once again, there is a polarity associated with the voltage drops that you see in a parallel circuit, the same way that we see that for a series circuit. A quick review of Kirchhoff's current law says that the sum of the currents going into a node is equal to the sum of the currents that come out of that node. So in this circuit here, we have some current that goes in. It splits and takes 3 branches. those three paths or branches will recombine right here. And I know that the total amount of current going in has to equal the total amount of current coming out. So if I add up these currents along these three paths, it will add up to the total current going into that node. In our last lab, lab 4, I believe, we learned how to measure current and voltage on the bench. Remember that in order to measure current, your ammeter has to be in series with the element you're measuring current for. That means we have to break the circuit. Here's a quick review of how we do that in multisim as well as on the bench. In multisim, your ammeter is placed in series with the element you want to measure. So if I want to measure the current that is going through R1 and around this circuit here, I need to put that ammeter in series. On the bench, we break the circuit. So this resistor right here was plugged in right over there, and that's where it's connected to the voltage source. The end of this resistor is pulled out, i.e. breaking the circuit. We put a wire in its place and we connect the DMM to that open connection point. So now that the ammeter is placed in series and we can read the current through that resistor. We also learned last week how to measure voltage. You're going to connect the voltmeter in parallel to the voltage you want to measure. In multisim, here's what that would look like. The voltmeter is connected on either end of the resistor to get its voltage. On the bench, we're connecting the DMM to either end of a resistor like this to get its voltage on the DMM. We also talked about measuring total resistance. In order to measure total resistance, you have to remove the power source completely from your circuit. It should not be connected in any way because it will affect your measurement. Once you remove the power source, you're going to connect the ohm meter or your DMM to the terminals where current would enter and exit the circuit. And then once you set that tool to measure resistance, you'll get a total resistance. In multisim, here's the multimeter connected to our circuit. Instead of a power source, we have the multimeter, and it's connected where current would enter and exit the circuit, and we have our reading. On the bench, this is the DMM. The power source has been completely removed, and we connect the DMM at the points where current would enter and exit the circuit. So now that we've done our review, we're going to apply all of these tools we've learned previously to now analyze a series parallel circuit. Series parallel circuits have a combination of elements wired in both series and in parallel. This is where your definition of series and parallel is going to come in handy. We're going to really have to rely on those definitions in order to analyze the circuit. So in the circuit shown on the screen, just as an example, we have a battery with a positive terminal, so we know current is going to flow through R1 and then through R2. Because there's only one path right here, there's nowhere else for current to go. There's one path. That means R1 and R2 are in series, and they have the same current. R3 and R4 are each on separate paths. The current is going to split, and some will go through R3, some will go through R4. So I know that these can't be in series because they are on two separate paths, and they're going to get different amounts of current. However, these two paths recombine right here. I have a split, two paths, and a recombination. That tells me that R3 and R4 are in parallel. Now, that means that R3 and R4 have to have the same voltage because that's a defining characteristic of parallel resistors. They have to have the same voltage. However, that voltage is not necessarily going to be the source. Whatever the voltage is of R3, it's also going to be the voltage of R4, but it is not by default whatever voltage is applied here. We have to make sure that we use Ohm's law, KVL, and KCL to determine every voltage and current in a circuit like this one. So R3 and R4 are in parallel with each other, but they are not in parallel with the source because I have two resistances right here along this path that are going to cause some voltage drops. If there's a voltage drop across R1 and there's a voltage drop across R2, all of the voltage from the battery cannot be across R3. So R3 is not in parallel with the battery. So to analyze the series parallel circuit, we must first combine groups of series resistors together, combine groups of parallel resistors together, and we call this the equivalent circuit technique. As we combine groups of series resistors and parallel resistors together, we'll collapse the circuit into one total resistance that we can use to find the current in the circuit, and then begin using our tools such as Ohm's law, KVL, and KCL to find other values. So when we start looking through our examples, we're going to rely on all of these tools in our tool belt for these examples. We're going to remember the definition of series, only one path for current to flow. The definition of parallel, two or more paths that diverge and eventually reconnect. We're going to remember that resistors in series must have the same current, resistors in parallel must have the same voltage, and then we're going to use Ohm's law, KVL, and KCL as we see fit to analyze each circuit. So at this point, you should have your notes out, and I want you to follow along with each one of these problems with me. We're going to start with example 1, where we're going to calculate the current through every resistor you see on the screen, as well as the voltage for every resistor you see on the screen. We're going to use KVL, KCL, and or Ohm's law at several points to check our work. So the first thing we're going to do is look for resistors that are in series or resistors that are in parallel. The first thing I notice is that R4 and R3 are in parallel. I know this because current splits, takes two paths. Here's path 1, here's path 2, here's path 3. We're going to worry about this path in a minute, but right now I have two paths where the current comes back together. R4 and R3 are in parallel. So I'm going to combine those using the formula for parallel resistance, and I'm going to relabel or rename that combination of these two resistors in parallel as Rx. So I'm going to call that Rx. Once I make that combination, I'm going to redraw the circuit showing Rx in the same place where R3 and R4 were. So once I've combined R3 and R4 into Rx, here's my new picture with that equivalent resistance shown right there. I haven't done anything with R1 or R2 yet. I'm just doing one group of resistors at a time. So now that I've combined Rx, I'm going to look for another group of resistors that I can combine together. Next, if I trace the path of current through the circuit, I can see that R1 and R2 are along the same path, and they must have the same current. If they have the same current because they're on the same path, they are in series. That means I can add them together. So I'm going to have a second combination called RY, where I add R1 and R2 together. Once I've made that combination, I'm again going to redraw the circuit. As you complete your notes, make sure that you are redrawing the circuit along each step, just like you see on the screen. Redrawing the circuit allows us to see what new relationships are formed after we make a combination. So now I have Rx and I have Ry. If I analyze how current flows through this circuit, I have total current flowing from the voltage source. It splits. Here's one path, here's a second path, and it comes back together. So Rx and Ry are in parallel, and I'm going to combine those using that same formula for parallel resistance. After I make that combination, I'm going to redraw the picture a final time, and I'm left with one resistance left in the circuit, RZ, my third combination. So I don't have any more resistors to combine. I have collapsed the circuit down to one resistance. That last resistance is now your total equivalent resistance in your circuit, or RT. We call that RT for short. So now I have the total resistance in this circuit when I combine all of those resistors together. I can use that total resistance and the source voltage to now find the total current using Ohm's law. So I know that the total current in this circuit is going to be my 18 volts divided by my total resistance. Now I know the total current in this circuit, 48.64 milliamps. So when we start analyzing a series parallel circuit, your first step is going to be to collapse all of those resistors into a single equivalent resistance, and then use Ohm's law to find the total current in the circuit. Those are always generally going to be your first two steps. Now let's look at how that total current translates back to every picture. Here's the picture we began with. Picture 2 after our first combination. Picture 3 after our second combination. And picture 4 after our last combination. That's an extra copy of the same circuit there. So let's look at how current travels. Total current flows through our final circuit like this. It becomes a series circuit. That same total current is going to flow into this node, split, and take two paths. If I go back even further, that total current again comes to this node, splits, takes two paths. And if I go back to the beginning, the total current that we've already found goes into this node, splits, and takes three paths. So when we find that total current in the circuit down here, we have not found the current for R4, R3, R1, or R2. That's why I'm translating that total current back to each picture that we made along the way, so that you can see that we're not just going to assume that the total current is the current for all of these resistors. It's only the total current coming from the source. That current is going to split and go in three different directions, and it's our job to find out how much current goes where. So when you find your total current, do not automatically assume that that total current is now the current for every resistor in your picture. Every circuit is different. It all depends. You have to trace the path of current and use our tools, KVL, KCL, and Ohm's law, to ensure you have the right current for each resistor in your picture. So I know that the total current goes this way and splits between R4, R3, and this branch over here. There are no voltage drops prior to this node where IT splits. That means that R4 and R3, they're in parallel with each other, and they're in parallel with the source. If there was a resistor right up here, or a resistor here, or a resistor here, or a resistor here, none of this would be true. But because there are no voltage drops until we get to this node and then the current splits, we can say that R3, R4 are in parallel with the voltage source. So I know the voltage for R3 and I know the voltage for R4. And now that I found the voltage, I can easily go use Ohm's law to find the current for each of those. So I'm going to label my picture with my voltage drop for R3 and my voltage drop for R4. So make sure that you're labeling your picture as well with your positive and negative terminals and the level of voltage drop. Now I'm going to use Ohm's law to find each current. I know the voltage for R4, I can find the current for R4. I know the voltage for R3, I can find the current for R3. Once I have these currents, I'm also going to add them to my picture. So here's R4, and here's R3. So I can see that IT splits. I know how much goes through R4. I know how much goes through R3. I know the voltage for R4. I know the voltage for R3. So I have two resistors done and two more to analyze. So here's my total current here. I know how much goes this way. I know how much goes this way. Now I can use KCL to figure out the third path of current, because I know how much went in and I know 2 out of my 3 total paths. So I can set up a KCL equation where I can say that 48.6 milliamps goes in, I know 18 milliamps goes this way, 23.44 goes this way, and I can subtract to figure out how much goes through R1 and R2. So I get 7.2 milliamps for the current for R1 and R2. Remember, they're in series, so they both have the same current. Now that I know the current for R1 and R2, I can find the voltages for R1 and R2 using Ohm's law. And I'm going to add those voltages to my picture as well. Now I'm going to use KVL to check my work. I know the voltage across R3, R4 are both 18 volts. I have a closed loop right here. I'm going to check my work by applying a KVL around this closed loop. If I did my work right, I can add up all the voltages using polarity around this loop, and that should equal 0. So let's say that I start right here and I go around the loop. If I start right here, I have a positive 3.6 volts plus 14.4 volts minus 18 volts. I'm back to where I started, so I set that equation equal to 0. And sure enough, if you add this up and subtract 18, you get 0. So I can see that KVL has helped me to verify my work is true. This is the process that we use to analyze a series parallel circuit. When you're done doing your work by hand, use multisim as a tool to check your work. Go build the circuit in multisim, add ammeters, add voltmeters, check your work. Make sure that every current you calculated by hand matches up in multisim. Make sure that every voltage you calculated by hand matches up in multisim. You might have a little bit of rounding error, but your answer should be very, very close to what you get in multisim. If they don't match, one of two things is wrong. Either your calculations have an error or your multisim circuit has an error. But you know that something is not right if they don't match up, and you can use that to go check your work and figure out where the problem is. Now we're going to move on to a second example where we're going to repeat the same process but with a slightly different circuit. So here's our circuit. We have a 2-volt source, 4 kilo ohm resistor here, 688 ohms there, and 0.52 kilo ohms there. First, if I look at the path of current, I can see that R8 has one path, R5 and R7 have a different path, and they are on the same path. They're in series. I can add those two resistors together and redraw my circuit. So Rx is my first combination. Rx takes the place of R5 and R7. Now I can see that R8 and Rx are in parallel with each other. They each have their own path, and I can use the formula for parallel resistors to combine those together. So R8 and Rx are in parallel. Combine them together, and you get 927.8 ohms. Redraw your circuit. I see that I only have one resistance left, and that is my total equivalent resistance in my circuit. Now I'm going to use RT, my total equivalent resistance, and the source voltage to find the total current. And there's my total current. So just to translate, our total current goes through our third and final circuit like this. That total current translates back to our second circuit by showing that it leaves the voltage source, splits between R8 and Rx. And if we go back to our original circuit, that total current splits right here. Some goes through R8, the rest goes through R5 and R7. So keep in mind when I make these replacements, I can use any one of these pictures to solve the circuit. For example, if I find the current through Rx, I find the current for what Rx replaced, which is the current through this branch. If I were to find the voltage for Rx, I have the voltage for what Rx replaced, which is the voltage across this branch. Sometimes we can use an intermediate step in order to solve for something we need from our original circuit. And that's how we're going to do this problem. Slightly differently from the last problem. It's a different technique, but it also works. All right, so if we look at our first circuit, there are no voltage drops from the source voltage to the node where we get R8. So R8 is in parallel with the voltage source because there are no voltage drops prior to this node. There's nothing to take away from the 2 volts. There are no drops. There are no drops here. The R8 resistor is in parallel with the 2 volt source. So I know the voltage for R8 is 2 volts. Then I can find the current for R8 by using Ohm's law. There's my voltage. There's my current. Make sure you're adding those to your picture as well. If I go to this intermediate picture right here, I can see that Rx is in parallel with R8 and the source. Well, I just found the voltage for R8, and I know that it's in parallel with 2 volts, which means I also know the voltage for Rx. So if I know the voltage for Rx, I can find the current for Rx using Ohm's law. So the current for Rx, oh, that should say voltage, not X right there. The current for Rx is your 2 volts divided by the value of Rx. If I find the current for Rx, I've also found the current for what Rx replaced. So what I've just done here is I've found the current that comes out of this node and goes around this part of the circuit. If I find that value, it is the same value that comes out of this node and goes through R5 and R7. So by finding the current for Rx, I found the current for R5 and R7 as well. So there's my current for Rx on my picture. The current through Rx is also the current through R5 and R7. And now that I have those currents, I can go find the voltages for R5 and R7. So that's going to be my next step. Before I do that, I'm going to verify that the current I found for this branch is right. I can do that using KCL. I know that the current going into this node has to equal the current coming out. So I'm going to add up the current going in, which is just 2.16 milliamps. I'm going to add up the current going out, which is 0.5 milliamps plus 1.66, and I'm going to make sure that they're equal. In this case, they are, letting me know that my work is correct. Now that I've verified that my current is correct for R5 and R7, I can use Ohm's law to find the voltages for R5 and R7. And once I have those voltages, I'm going to add them to my picture as well. Now that I have those voltages, I also have a closed loop right here that I can use KVL to check my work with. So if I decide to do a loop around here and make a KVL equation, here's what it would look like. Let's say that I start right here. I have a positive 1.14 volts plus 0.863 volts minus 2 volts. And I get 0.003. Something really, really close to 0 is okay because you're going to have some rounding error. So you know it should be about 0. It should be very, very close to it. And this is definitely close enough. So KVL has helped me to verify my work. When you're done, go check your work in Multisim. So we can see that my total current was 2.16, and in Multisim I got 2.155 milli. We can see our voltages here, and we can see that everything matches up with what we calculated, save for a little bit of rounding error. Now there's a third example in your notes. I'm going to leave that one for you to do on your own. Try to apply the same principles that we've done in these first 2 examples and see if you can solve that one on your own. If you can't, feel free to reach out to me with questions or to bring that example to class and we will go over it. But I want you to try some independent practice with that third one in your notes. For the last example in this video, we are going to look at the circuit that we're going to build in Lab 5 and we are going to analyze it. So if you look at your lab manual for Lab 5, we're building a series parallel circuit and we're going to apply different levels of voltage. But for the analysis part, we're just going to assume that the source is 2 volts. And we're going to do everything we just did on the first 2 examples for our circuit for Lab 5. So I'm going to start by looking for groups of resistors that I can collapse. Things that are in series or things that are in parallel. So the first thing I want to point out is we have the current flowing from V1 through R1. It splits. Some goes through R2, some goes through R3 and R4. Some students are tempted to say that R2 and R1 are in parallel, but they're not on 2 paths that split and come back together. So R1 is on this path. The current splits. Here's path 1. Here's path 2. Here's where path 1 and path 2 meet. So these 2 paths are what are in parallel. R1 and R2 are not in parallel. But before we can combine these 2 paths, let's first combine R3 and R4. They're in series because they're on the same path and have the same current. Let's add those up and find our first combination, which we're going to call Rx. Redraw your picture. And now I can see that R2 and Rx are in parallel. We have two paths where the current splits and comes back together. So I'm going to make my second combination, I'm going to call that Ry, where I combine Rx with R2. And when I'm done, redraw the picture. Now I can see that R1 and Ry are in series. They're along the same path and must have the same current. So I'm going to add R1 and Ry for my last combination. I now have one resistance left in the circuit, and I know that that is my total equivalent resistance, or RT. Now I'm going to use Ohm's law to find the total current in my circuit. So in this case, we get 1 milliamp. So there's my total current. I can see that the total current is also the current for R1 because there's no other paths. The R1 is on the path where total current exits the source. So I know the current for R1. I don't know the current for R2 or R3 or R4 yet, but I do know that the total current is the current for R1. So then I can go find the voltage for R1. And I'm going to add that current and voltage to my picture. I can now use KVL to find the voltage for R2 because I have a closed loop right here. So here's my equation. 0.68 volts plus whatever the voltage drop is here minus the source voltage here. It's going to give me 0. I can use that equation and solve that for R2. So there's my voltage drop for R2, 1.32 volts. Then I can use that voltage drop to find the current for R2 using Ohm's law. So there's my current and voltage for R2 added to my picture. Now we have to tackle R3 and R4. We have several options. We could use KCL to figure out how much current goes this way. Or I know that I can add up R3 and R4 together. And if I go back, for example, when we added R3 and R4 together, we got Rx. If I can find the current through Rx, I can find the current for R3 and R4. So you have more than one way of looking at your next step. As long as you're applying our laws and rules appropriately, it's fine to have a different path than someone else might have done it. So we have our current and voltage for R2. I'm going to use KCL to find the current for R3 and R4. 1 milliamp goes in, 0.281 goes down through R2, so I know the rest must go through R3 and R4. Now that I know this current, I can find the voltages for R3 and R4 using Ohm's law. And once I've done that, I'm going to add them to my picture. And last but not least, I can perform a KVL around this closed loop to check my work. I know that plus 1.079 volts plus 0.237 volts minus 1.32 should give me something very close to 0. And if I add those up, I will see that. So there's my equation for this loop. I also did a KVL equation for the first loop as well. That's what this equation is down here. We did this equation earlier. And here's my KVL for the second loop right down here. So KVL, KCL, and Ohm's law are all tools that you can use to find a value and or check that a value you've already found is correct. When you're done, we're going to check our work in Multisim. And this is going to be part of the lab that you build this circuit, set the voltage source to various levels, and then get these readings. And once you've done this work in multisim, you're also going to build this circuit on the bench and use the DMM to measure all of these voltages and currents. All right, that's the end of this video. If you have questions, please reach out to me via email, Canvas message, or send me a comment on this video and I will respond.